I have to look at the
So let me
YouTube
turn it
video.
over to John, and where everybody looks like everybody's muted, so that's good.
Okay. All right. Ready to go?
Yes.
All right, let's go. All right, today I'll be giving a brief introduction to active flow control. And everyone can see my screen?
Yes.
And Bruce, yep, and Bruce, you're recording?
Yes.
Cool. All right, when I talk about active flow control, mainly what I'm going to be talking about is adding energy and basically exploiting flow physics to accrue an engineering benefit. Now, to understand active flow control, it's really important first to understand turbulence. Now, qualitatively, I think that most people know what turbulence is. If you look at the flow on the left versus the flow on the right, the one on the left is pretty obviously laminar flow. There are really no eddies. It's a very smooth flow. The velocity is very constant over time. On the right is actually a sketch of a turbulent flow as drawn by Da Vinci. He actually sketched several of these turbulent flows. This one looks like some sort of a sink or something like that, just water pouring in, and you can see how it's churning. It's chaotic. There are lots of eddies. So qualitatively, yeah, laminar flow, turbulent flow, pretty obvious, right? But what do we mean by that in a scientific sense? Turbulent flows have several key differences from laminar flow. First of all, they're three-dimensional. You really cannot have a two-dimensional turbulent flow. Second, they have multiple scales. And by that, I mean they have eddies or vortices of many, many, many different sizes. I'll touch on that a little bit more in the following slides. Third, they have good mixing. If you want to mix two different chemicals or mix hot water and cold water or transfer momentum from one fluid to another, you really require turbulence to do that, to get the good mixing. And finally, turbulence requires some sort of shear to produce the turbulent kinetic energy, also known as TKE, which I'll refer to throughout this. What I show here is a very simple flow called Couette flow. And this is created just by moving. It's a flow between two walls, except you move one wall. And when you do that, you get stress or shear between the two walls. So it's basically just a velocity gradient. It's basically just a velocity gradient, I guess is what it comes down to. A velocity difference over a spatial distance. The Mount St. Helens eruption really illustrates all the qualities you would think of in a turbulent flow. First of all, it's three-dimensional. You can see that these bulges of hot ash are moving in and out of the page, left to right, up to down. It's very three-dimensional. There are multiple scales. And by that, I mean, if you look at, for example, this looks like a big vortex, or this. And these are almost on the same order of magnitude as the width of the crater itself. The crater of Mount St. Helens today is about, I believe, 2 kilometers by 3 kilometers. This looks like it was sort of in the midst of the meltdown, where it was more, maybe, say roughly a kilometer in diameter. If you go down and you looked at the smallest scales present in this flow, you would have eddies on the order of a millimeter or even smaller than that, on the order of hundreds of microns, for example. So you're really talking about, in this case, maybe 5 or 6 orders of magnitudes between the largest eddies and the smallest eddies, which is indicative of a very well-developed turbulent flow. Good mixing, as I mentioned before, you can kind of see all the dust and the clouds and the soot are all mixed together, so you don't have really a whole lot of clean air in there. And shear. So again, because this was an eruption, you kind of had a mean velocity going up and out, and then out here you've kind of got no flow, so you've got a shear between the high flow in the center and no flow on the outside. there's something, a concept of an energy cascade in turbulence. Turbulent kinetic energy, or TKE, is passed from the larger eddies to progressively smaller eddies. And they're really passed from eddies that are slightly smaller. So you don't have, the huge eddies like I showed in Mount St. Helens interacting with the teeny tiny sub-millimeter eddies. You're really kind of passing energy from progressively smaller and smaller to progressively smaller and smaller energies. Again, turbulent kinetic energy, because I haven't fully defined that here, it's basically the energy in the flow per unit mass due to turbulent fluctuations. So these little u's are velocity fluctuations, and you square those and sum them up over the 3 dimensions. And that's basically your turbulent kinetic energy. Once you get down to the smallest level of turbulence, it doesn't just keep going forever. It actually reaches a point where the eddies are at the point where viscous heating and viscosity becomes important. So in the smallest eddies, you get a phenomenon called turbulent dissipation, epsilon. And that's the rate at which viscous shear stresses convert the turbulent kinetic energy into heat. And really, you don't get any scales below that. So again, you have energy being produced at the largest scales, passed to progressively smaller and smaller scales, till finally you get to these smallest scales where this turbulent kinetic energy is turned into heat. All right, let's talk a little bit about the transition from laminar flow into turbulent flow. Now, I should preface this by saying that dozens, maybe hundreds of engineers have gotten their PhDs just studying turbulent transition, how laminar flow transitions to turbulence. I'm going to cover this in about 3 or 4 minutes, and so it's obviously a fairly general, not very detailed overview of this, but it's important to understanding active flow control. So I wanted to at least cover it to some degree. All right, there's your turbulent jet. You notice that it was laminar just coming out of the jet nozzle. And by the time you get out here, it doesn't quite look like Mount St. Helens, but it's obviously a fully turbulent flow. Let me highlight that a little bit. And so the stages of turbulent transition are initially just downstream of a boundary. You have fully laminar flow, and then there are instability waves that start to develop in the shear region. So here you've got shear between the high-speed jet and the still ambient air. And these tend to be sinusoidal at first, sinusoidal 2-dimensional instabilities. As you go further downstream, these 2-dimensional instabilities start to develop some secondary 3D instabilities. And so here we can see that these 2D waves are now starting to get some undulations. Maybe they're a little bit oblique. They're not going straight downstream. They're going downstream with an angle. If you look, there are some streaks in the flow. Those are actually streamwise vortices. Streamwise vortices that form between 2 successive 2-dimensional vortices. And as these things get stretched, they can break down further and further. Finally, you occasionally get a turbulent burst. So most of the time, yeah, pretty laminar, then suddenly, boom, a big burst of turbulence. This is actually pretty similar. Well, I won't say it's similar, but 2 weeks ago, Ed Friedman talked about chaos. Turbulent transition is a chaotic process. The Navier-Stokes equations that cover fluid mechanics are highly nonlinear. And so when you start getting into turbulent transition, you start out with some regular 2D instabilities quickly becoming chaotic and unstable. Then as you get further downstream, then you've got the fully turbulent flow. Does that sort of make sense to everyone?
yeah, John, why does the laminar flow transition into turbulence? Why does it just keep going laminar?
That's probably beyond the scope of this paper. I mean, of this presentation. That's that's kind of the thing that dozens and hundreds of people have studied. But it turns out, in a nutshell again, you can linearize the Navier-Stokes equation and find out that there are some unstable eigenfrequencies and eigenmodes, which are basically just a linear instability. As those get larger and larger, the linear approximations no longer hold. You start to get susceptibility to a 3D instability. And then when those instabilities get large enough, then you're kind of fully in the chaotic, non-linear region where turbulence can just sort of burst out.
Well, by the same token, when it's in the fully turbulent flow, is that a stable situation? Or is it just too big?
Yeah, flows typically don't go from turbulent back to laminar flow, if that's what you mean. But obviously it's a very chaotic motion where you can't predict from one instant to the next what the flow will be at any given location.
John, one quick question. You mentioned that it has to be three-dimensional.
Yes.
Is it not possible to conceive of turbulence in 2 dimensions only?
Not that I'm aware of. If anyone could come up with a counterexample, I'd love to see it, but I've never seen 2-dimensional turbulence.
Yeah, I think that's true, and it has to do with the degrees of freedom when you get into 3D.
Mm-hmm.
So I have a question. Bernoulli's equation would
Yep.
cease to exist at that point?
I'm sorry, what was that?
Bernoulli's equation would cease to exist at that point?
Bernoulli's equation is a simplified version of the Navier-Stokes equations. Yeah. So.
Can you define laminar, John?
Laminar flow, I talked about, if I go back one slide, I don't want to go back too many slides because otherwise I'll never get done. So I talked about turbulent kinetic energy, where you have velocity fluctuations. And the turbulent kinetic energy is basically the sum square of all the components of that. To me, a laminar flow is just one where those velocity fluctuations are very, very low.
Okay.
So typically if we're making a wind tunnel or something and we want nice laminar flow, then those velocity fluctuations will be on the order of 0.5% of the mean flow or something like that. All right. Let me move on because this is, again, just sort of the background to the main meat of the talk, which is active flow control. But hopefully everyone at least sort of understands this process because it is important. All right. All right, so what do I mean by active flow control? What I mean is introducing a small amount of energy at the beginning of the shear region of the flow. And again, showing the same image, which I think is a great illustration of the turbulent transition. So what's not shown here is there's some sort of a nozzle, right? So there's a nozzle and this jet is emanating from it. So typically you would add some sort of energy right at the nozzle. You kind of need a spot to mount your hardware, frankly. And so most of the time people put whatever they're using to affect active flow control, basically somewhere in this location, right at the beginning of the shear region of flow. The goal is to modify this turbulent transition process, and by so doing to accrue some sort of engineering benefit further downstream, whether that's enhanced mixing, reduced noise, increased noise, decrease, some sort of engineering benefit further downstream once you've introduced this active flow control.
When you put energy, can I ask a question? When you put energy at the nozzle, is it across the entire nozzle or just some point at the edge of the nozzle?
I'll get to that.
Thank you.
Yep. There are 2 approaches to active flow control that I will talk about here. There are many, many others that have been done by, again, dozens of researchers. And again, going back to this little cartoon I showed about the energy cascade, there are 2 real approaches. The first is to exploit jet instabilities. And that's typically done by putting in energy to influence the largest scales of the turbulent flow or the transitional flow. This could be done for something like vectoring. This could be done to enhance large-scale mixing and entrainment into jets. There are lots of different applications of that. There's a second approach that I'll talk about, which I personally think is a lot more interesting. Although I guess I'm going to talk about a little bit less, but it's also pretty interesting. And that's where you actually introduce energy at these smallest scales of the flow, bypassing all of these instabilities in order to directly enhance small scale mixing in your flow. Most of the experiments I'm going to talk about today were conducted in an air jet facility with a square nozzle. It's fairly standard in fluids labs across the country. You'll have some sort of a blower, foam, create a plenum. The speaker I didn't use, so I probably should have crossed that out. And then it's basically just a small wind tunnel. So I've got honeycomb, foam, more screen. This is all basically to make the flow as laminar as possible before it enters the square tube and then is basically expelled into the lab. This tube was about 1.5 inches square. So, just a small thing. The flow velocities we used were fairly slow. I mean, it isn't like a supersonic jet or anything like that. 2 sets of experiments I'm going to show here. One was done at 4 meters per second, and the other one was done at 6.5 meters a second. All right. Now, I was asked about how you actually introduce your active flow control. And so in this case, we used 4 piezoelectric blade actuators. And you can kind of see these in a cross section and a frontal view here. These are just mounted right at the front or the exit of the square tube or the square nozzle. And these are basically just a piece of stainless steel with 2 pieces of piezoelectric material on either side. So they're sandwiched. And you apply an oscillating voltage to these and they tend to oscillate. They are very much a resonant structure. So you really need to run them at their resonance frequency or you don't see much of anything at all. Everyone kind of get that, what these actuators are? The square nozzle happened to work very well with these piezoelectric actuators, right? Because you could just put 4 of them around the nozzle and affect the jet that way. All right, moving on. This is it's called a Schlieren photograph. I think I showed some of these earlier, but this is just an image of what the flow looked like without any active flow control. And it shows some of the same characteristics we saw in the other images. It's a square jet, so maybe it doesn't look quite as canonical as some of the other ones, but you see some of the same features, right? You see nominally laminar flow coming out of the nozzle. You see the 2D instabilities. Then as you go further downstream, you start to see turbulence start to develop. As I mentioned, we used piezoelectric actuators for the active flow control here. The actuators had a resonance frequency of 500 hertz. And as I mentioned, the Q was very sharp on these. So trying to run them, even at like 480 hertz or something like that, you basically get no output. So we really had to run them all at the resonance frequency. The jet we were using happened to have an unstable frequency of most unstable frequency of about 16 hertz. And what that means is if you look at the passage rate of the vortices or the 2D instabilities just downstream of the jet nozzle, it was approximately 16 hertz. So there are some advantages to trying to put in instabilities that are close to the natural frequency of the jet, because then the jet amplifies those frequencies. And we, because of that, and because the actuators had a natural frequency or resonance frequency of 500 hertz, we had to use this amplitude modulated signal, which worked pretty well. the actuators responded to this pretty well. This was measured with a microphone set at the center of the jet. And basically we would just kind of tune these up, get them in resonance, and then just verify that they responded to the modulating signal, which in this case was 16 Hertz. The nice thing about these piezoelectric actuators is they were small, cheap, and used very low power. So they're great for a grad student to use, and theoretically they're good for practical applications as well for those reasons. We could excite different jet instability modes by changing the phase relationships between the actuators. I don't want to go into a whole lot of detail on this, but we could put in a spiral mode and basically just run each actuator 90-degree out of phase with each other. But you kind of get this standing wave mode if you superpose two counter-rotating helical modes. So, if you imagine you're putting in a mode that is going clockwise and one that's going counterclockwise, really you just get a standing wave. And some of the key ones we looked at were mode 0, where all 4 of the actuators were running in phase. Mode ±1, meaning we were superimposing a mode +1 and a -1. And the standing wave was basically these 2 actuators were 180 degrees out of phase with these 2 actuators. And then a mode ±2, so basically you're spiraling around twice as fast. And what that turns into in terms of a standing wave is that the top and bottom actuators are 180 degrees out of phase with the 2 side actuators. The cool thing is then you can go downstream and measure the response of the flow. It happened to be done with hot wire anemometry, but we could have done any other high frequency response flow measurement technique. And what you see here is the time-dependent streamwise velocity at a distance of 4 jet diameters downstream. And I'm plotting this as a function of time, and I'm showing in each case 3 phases of the modulating frequency, the 16 Hertz modulating frequency. I'm showing 3 cycles of that. And so mode 0, where all 4 actuators are in phase, it kind of puffs up and necks down, puffs up, necks down. Mode ±1, you can see it starts to wave back and forth along that diagonal corresponding to the actuators. Mode ±2, again, it necks down, it squashes out horizontally, then squashes out vertically, and vice versa. So it's kind of undulating back and forth over time. And then finally, mode -1 is a helical mode. Hard to tell in this picture, but it's basically corkscrewing. When you do this, it actually has the effect of changing the mean or the time averaged velocity profiles, which is pretty interesting. And again, this is 4 jet diameters downstream, so you're a long way away from the actuators. So the unforced flow, as you would expect, is square. Mode 0, it ends up looking more like a circle, a circular jet. Mode ±1, again, you can kind of see this oval stretched along the diagonal. And mode ±2, it ends up looking more diamond-like rather than square. Everyone sort of understand that? Makes sense? If anyone's totally lost, this is time to stop me. All right, moving on. All right, so that's all well and good, but what's it good for? You've done something pretty cool, but is there any application for this? Well, we came up with one working with McDonnell Douglas. So the C-17 cargo plane was just coming online at about this time. Most, or at least many airplanes have thrust reversers on the bypass flow or the fan flow. When you land in a plane and then, you see the things on the engines kind of flap out and then the engine runs real fast and you slow down, right? That's due to the thrust reversers. And so the C-17 is no different. It had thrust reversers on the core flow or on the bypass flow that's used for slowing down the aircraft and maybe even maybe even reversing it, backing up if needed. But here's the interesting thing. It also had thrust reversers on the core flow. And these actually weren't really needed to slow down the plane or to stop the plane. They were actually done just to protect the load masters, this guy here, when they do loading and unloading with the engines running. So the concept of this thing, the operational scenario is the C-17 lands, they leave the engines running, they unload the aircraft and they take off again, right? But to keep these guys from being like basically cooked, especially in a hot ambient environment, they really needed thrust reversers on the core flow. So what if we could replace the core thrust reversers with active flow control and disperse this core flow so it's no longer hot enough to actually like burn or damage these guys? If you could do that, you would save $1.2 million per aircraft. You would also save 1,200 pounds of weight just in these core thrust reversers. So it's very enticing. Actually got a little write-up in Aerospace America back in the day. So let's try that. So what did we do? We took the piezoelectric actuators that we had used before, and we put them around a bigger nozzle. It wasn't as big as the real one used on the C-17, but it was bigger than the one in my lab. And we ran it quite a bit faster. Instead of 4 meters per second, I think we were running at, God, I want to say like 80, 90, 100 meters per second. So, you know, kind of getting in the velocity range that they would actually be running on the C-17. So what was the effect of this? Let's take a look. If my video plays. If it doesn't, I'll be very, very sad. All right, so this is a Schlieren photograph, and this is your baseline flow. So no actuators running. You notice we have 8 actuators around it instead of the 4 that I used in my previous experiments. Now just the top 2 or the top 4 actuators are running. See the huge, large structures coming. Now all 8 actuators. This is mode ±1. You can kind of see these oblique and zigzag vortical structures, and look how much the jet is stretching. Run that again real quick. I don't know if everyone got a good look at that, but maybe I won't run that again. But it had a pretty noticeable effect on the flow. And then we wanted to look and see, well, that's great, but does that actually disperse the hot plume? So we heated up the plume to, I think, something on the order of 200 C or something like that. We used a primitive infrared camera, which I think, you know, at least Mr. Miller and Mr. Ellison will get a kick out of. And we basically ran the same experiment. Now, I do need to apologize because for some reason, the previous experiment, everything was going left to right. Here it's going right to left. So it's a little bit confusing. So this is flow running, no actuation. You can see the big plume. Again, it's an Agema camera. Now we're just running the top 4 actuators. And then we're later going to turn on the bottom 4 actuators. So we're running mode ±1. Okay, all actuators off again. And now mode ±1. Look how the hot plume almost disappeared. Quite a bit shorter. The region, you know, maybe halfway through here really doesn't show much hot gases at all. So it looked like it was feasible. It looked like it may actually disperse the hot plume. This might be something we could use.
Hey, John,
Yeah.
what's the ring represent? Is that the quadrants where the hot air goes, or what does it do? So I'm not sure how to read this.
This ring?
Yep. Yes.
Yeah, so that's just a cartoon showing the jet nozzle. And we had 8 actuators. So 1, 2, 3, 4, 5, 6, 7, 8. And when they're not running, there's no fill in those segments. And when they're running, white and red indicate 2 different phases.
So are we looking aft on the engine nacelle, or is this just a representation of where the hot air comes out?
Oh, got it. Yeah, yeah. So so it's a side view of the jet nozzle. And this is just a cartoon to show what modes we're running.
So how many jet nozzles are we having on that particular engine?
Well, there was just, so this wasn't an actual engine, it was just a lab experiment. And there was just one, yeah, there was just one engine, or just one nozzle.
Mm-hmm. Got it. Okay.
Yep. Cool. Any more questions on that? All right, let's go.
Question. So
Yeah.
are you adding turbulence like right by the engine or where the engine would be?
Not so much turbulence. We are just exciting the 2D and the 3D instability modes. And so that's kind of the beauty of this approach, is you can put in a relatively small amount of energy near the jet nozzle, and it's actually amplified by the flow, and it actually gets to be more and more of an effect as you go further downstream.
Okay, thank you.
Mm-hmm. All right, so centerline temperatures also show quite a drop. So this is basically just running some kind of a temperature probe. I don't even remember what we used at the time, basically down the center line of the jet. And the reference in cyan shows that it's very hot, and the darker blue shows that, well, it got a lot cooler. So it looked like, again, it was very, very interesting. The experiments, the feasibility experiments were successful. This looked like a way that we could eliminate those core thrust reversers on the C-17. Did it ever happen? No, it never actually happened. I think that the risk of doing that, and kind of the risk of the unknown, probably outweighed the potential cost and weight savings of doing so. But it was a cool idea, and it was an application that almost had some traction there for a little while.
Hey, John, why don't they just shut the engines off when they're loading and unloading?
Because they want to land and then take off really quick. They don't want to be sitting there on the ground and then have to start their engines back up.
Now, those engines, when they're more or less idling, are still a tremendous amount of horsepower. So what kind of power would have been needed to cause the distortions that you have shown?
Again, what we were using was I don't know exactly how close it was to being to scale. It was, it wasn't like 100th scale. It was probably, 5th scale or something like that. These things don't use a lot of power. And again, the advantage to this is you're actually relying on the fluid flow to amplify the disturbances you put in to get the benefit. So you don't need to put in as much energy as you would think you would.
Thank you.
Mm-hmm.
John?
Yeah.
Is this then kind of similar to like a turbocharger where you're piggybacking on top of a different mechanism?
No, I don't think I would call it that. No.
Okay.
No. No, I mean, this is basically just you're taking advantage of something that would have happened anyway. You're just kind of giving it a little bit of shove to make it happen sooner. I guess to put it into something that I'm sure you're familiar with, and probably other people are, they put riblets on airplane wings, right? And what that does is it's passive flow control. What that does is it introduces three-dimensional vortices to help keep the flow attached to the wing. So this is more like that.
So it's like a stall kit sort of. I get it.
Yeah.
Okay.
All right. All right. So I mentioned there were two different approaches I was going to talk about today. Here's the other one. So it's also possible to add high frequency energy to the flow directly. So in this case, I took off the 500 Hertz blade piezoelectric actuators and came up with these like insanely loud, absolutely deafening 5 kilohertz actuators. And I'll show a picture of these, or at least a cartoon of them in a later slide. Did not end up modulating that at all because I wanted to put in a higher frequency. So again, the natural frequency of the flow is around 16 Hertz. I was putting in around 5 kilohertz. So something on the order of 2 or 3 orders of magnitude higher than the natural frequency of the flow. So kind of down again, in this region of the flow, we were introducing disturbances that correspond to, it's actually called the Kolmogorov scale, but it's the smallest scale of turbulent motion. And what we were able to show, and I'll show that in following slides, is that we were able to introduce small scale mixing directly by bypassing the energy cascade. So in the previous examples, I was using the natural instability of the flow and the natural energy cascade to get a benefit. Now I'm bypassing all that. I'm just adding energy directly to the small scales of the flow. Again, I use the same air-jet facility. As I mentioned, the actual actuators were different. So I used a wedge actuator, actually 2 of them. They happen to be about 3/4 of an inch wide. And so put 2 of them down here, just on one side of the square nozzle. And if you do your Schlieren photograph again, and you look at your unforced flow on the left and the forced flow with the actuators running on the right, I don't see much of a difference. Do you? I don't. So you can maybe, if you squint at it, you can imagine things are a little bit different. And I'll get to that later when we look at the data. But it's interesting that you can put all this energy into the flow and the mean flow doesn't look that different. So what's going on? All right. I'm going to skim over this a little bit, but this is called a power spectrum. And so what you do is you take the time sequence of velocity, you do a Fourier transform of it, and you plot it. And so this is the power spectrum of velocity. As a function of frequency in Hertz, and this is just the turbulent kinetic energy, basically. And this is for the unforced and the trace above. I actually offset the trace above by, I think, like 3 orders of magnitude just to separate them out. It's not really that much higher. But you can see the unforced flow has this characteristic shape to it, where especially if you go further downstream, it has this flat region with a slope of -5/3. This is called the inertial subregion of turbulence. But what you also see in the flow, the forced flow, is you see the 5 kilohertz you're putting in. On the left, we're 5 centimeters downstream, a very strong peak, and also one at much smaller one at its harmonic. And you would think, well, that's such a small scale, the Kolmogorov scale, that's going to be attenuated. Well, you know what? It turns out it actually really isn't. You go to 10 centimeters downstream, you still see this 5 kilohertz peak in the flow. So that was kind of counterintuitive to us. So what else? There's something called turbulent dissipation, and it's denoted by epsilon. And that's basically just the rate at which the turbulent kinetic energy is being turned into heat. Remember, I had that energy cascade. The last step is the smallest vortices turn the turbulent kinetic energy into heat. That's called turbulent dissipation. So I'm plotting that here. Here I'm just kind of doing a false color contour plot of turbulent dissipation in the lower half of the jet. This is for the unforced case, and this is for the case where we're running this actuator. The forced case, we're running the actuator at 5 kilohertz. Look how much more turbulent dissipation you get in the flow when you run this actuator. And it's not just right by the actuator, it's all the way through the regime of measurement. And if you plot this on a linear scale now, or on a log scale, and here I'm basically just looking at the center line along y equals 0, so going do 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 do. You see that this is close to the actuator. This is more than an order of magnitude higher when you force it, and even down as far downstream as we measured, which was 10 centimeters, it's still on the order of 3 or 4x higher in the forced case than in the unforced case. So we're obviously doing something to the flow. We're putting in these smaller mixing scales, and it's not just right by the actuators. Okay, so pop quiz. What do you think this is going to do to the turbulent kinetic energy? Increase it or decrease it?
Increase it?
Increase it? Do we have another guess?
I would also say increase.
Okay, sort of. So let's go. Let's move on. So here's what actually happened. So here I'm showing the turbulent kinetic energy in the forced and the unforced layer. And what we see, if you look really close to the actuators, you're right. This is increasing the turbulent kinetic energy. You're throwing in a lot of energy. But remember, the wavelengths or the size of the vortices we're putting in. We're putting it in the area where it actually dissipates and sucks energy out of the larger scales. So what's really cool about this is, yeah, right by the actuator, you do have an increase in turbulent kinetic energy. But as you go further downstream, look, this is actually lower than the unforced case. So when you plot the two, upstream, the forced flow, yeah, it's got about 20 or 30% more kinetic energy, turbulent kinetic energy than the unforced case. But by the time you get downstream, it's got 20 or 30% less turbulent kinetic energy. These small vortices that we're putting in the flow are just kind of like sucking the life out of the flow, which again was very, very cool, I thought. Again, it was something that was pretty much unexpected. No one really thought that that's what would happen if you put these this kind of high frequency disturbance in the flow.
So how are you measuring that again, John?
I measured this just with hot wire anemometry, which for those of you who aren't familiar, you basically just take a very small wire, you heat it up, and then you monitor the voltage required to keep it at a constant temperature. So it measures velocity, and it measures it with a very high frequency response, which is needed for this type of measurement.
So it goes completely across the flow in one direction.
Well, so what I did is I had the sorry, probably could have clarified that a little bit. I had the one hot wire, but then I traversed it. So I would just go boop 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 boop, beep 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 beep, boop 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 boop, and just collect data over a span of several hours.
Yeah.
So
okay.
Yep.
How many times did you run this?
What do you mean? Are you asking if it's repeatable?
Yeah, you're showing a picture, but was that just one run?
Well, this was probably taken over the span of several days, actually. So I would run and then I'd go home for the night and I'd come back and reset it up and run it. So it wasn't just like a snapshot.
And the pictures were the same all the time?
They were reconstructed from a time sequence of data. So this is just a false color image of data computed from velocity data taken from my hot wire.
Okay, so this represents all the times you ran it.
Yeah, correct. Yep.
Okay.
Yep. All right. So
did your actuator get really hot?
In this case, it wasn't heated. So this jet was actually not heated. This was just the lab jet running with room temperature air. I'm sorry, do you say the actuator or the hot wire?
Actuator.
They heat up a little bit, but not that much. No, no,
Okay.
no.
Yeah, everything's so empirical in that business.
Yeah, yeah.
So
No, I mean, they were, you know, they were, as I mentioned, all of these were running at their resonance frequency, and the Q was very sharp. And what that means is you're not actually dissipating any energy in the actuator, or very, very little.
So does the mass flow rate of the air change?
They typically do. I did not actually calculate that in these experiments. They typically do because they entrain more air from the ambient. And I suspect that if you look at especially the previous set of experiments, yeah, the mass flow would increase. Yep, absolutely. All right, so what's the application of this? Well, all right. What if you just did this? You did this awesome high frequency stuff, but you didn't need this, you know, huge experimental apparatus with basically a small wind tunnel and a 4 meter per second air jet. So some of the people I worked with, my PhD advisor, and then some of the students who followed on as his students after I had left, started looking at just that. So what they did is they developed something called a synthetic jet. And synthetic jets are high frequency active flow controls without any base flow. And so what they are is you can just see a hollow cavity with a piezoelectric actuator. And the actuator, doesn't show it here, but it moves down, sucks air in, and then it moves back up and it ejects the air. Now these things are actually running at frequencies comparable to the high frequency actuators I showed before, something on the order of a few kilohertz. And when you look at the velocity profiles, you can see them just, you know, ejecting air, sucking air back in, ejecting air, and so on. They use this to cool a couple of, they basically use this for cooling applications. And actually they were able to commercialize it. They developed a small company. They created something called SynJet, which used these turbulent pulses of air for electronics cooling. And if you were happened to be browsing DigiKey, you know, 5-10 years ago, you could actually buy these things. I don't know if they're still being made, but they, you know, they work. You would basically put a small heat sink right next to this thing, put it on a hot component or a hot laser diode, something like that, and then you blast it with these turbulent pulses of air. You don't need a fan, you don't need any of this other stuff. Again, I don't know that this really took off, but it was kind of an interesting application of active flow control.
John, at 5K, to have to listen to it would drive you crazy, wouldn't it?
Yeah, it did. Oh my God, yes. I literally, I mean, I think my hearing is damaged, not from those, but from these guys. I mean, it was 5 kilohertz. You know, you would wear, you'd wear, earmuffs and earplugs and whatever, and you just couldn't block it out. It was awful. So I don't know, honestly, what frequency these SynJets run at. I suspect, you know, if it was above 20 kilohertz, then it would be out of the human hearing range and it wouldn't affect you. And that's certainly possible with this type of technology.
Just driving.
How much air can you push out with the SynJet? Because it's convective cooling, right? That depends on the mass of the air.
It does. That's definitely a limitation of it. Yep. And I don't know the exact amount, honestly. I do know that, like many of these other jets, it tended to entrain ambient air. So it wasn't just the air coming out of this tiny little hole. It was all the air that kind of got sucked along with it. So
I looked, John, and it's available. It's being used to cool high-powered LEDs, apparently, and in cooling things in cloud computing. So it's a really cool idea. It's really being used.
Yeah, there you go. All right. So That's basically all my talk. I do want to just kind of reinforce some of the key takeaways. What the heck? Okay. And they are we talked about the characteristics of turbulent flows. They're three-dimensional, they're multi-scale, they have good mixing, and they have shear. We talked about the process of turbulent transition, where you have laminar flow that goes to 2D instabilities, to 3D instabilities, turbulent bursts, and then full turbulence. And talked about a couple different methods of implementing active flow control. These square piezoelectric blades around a jet, and then the zero mass flux syn jets, and some of the benefits that can be provided. Reducing hot plumes from the C-17 was one application, and then cooling electronics with these little syn jets is another. All right, are there any further questions?
John, it would seem to me that it might be applicable to mixing of the fuels in a liquid rocket to get better combustion or faster combustion. And worst case, for this massive ordnance air bomb, this MOAB, where you're mixing, who knows, gasoline or something with massive amounts of air.
Yep. Yeah, absolutely. Yep. Yeah, I mean, mixing of chemical species is one of the one of the key applications of this.
Cool.
So for the second experiment where you're looking at turbulent kinetic energy in forced and unforced layers, why does the heat diffuse sooner in the second one? Where does it go?
It wasn't so much that the heat was diffusing, it was that the turbulent kinetic energy was turning into heat. I did not, to be honest with you, I haven't actually run the numbers to see if that amount of difference in kinetic energy could actually be measured in terms of a temperature rise. I think it would actually be pretty small, if that was the question.
John?
Yeah.
Yeah, just like a small observation on this, and then a general question. I don't know, but I look at this picture, and it seems like close to the nozzle, the turbulent kinetic energy is higher. It's a lot more yellow.
Yep.
And so, in fact, in answer to the previous stuff, it's probably in some sense being conserved. It's just where you dissipate it, close to the nozzle or far.
Yep.
And then, but then the question: do we know why it works? I mean, it's just so neat. But do we know? Is it just the Kolmogorov cascade, or is there something far more?
I think it's just that. This I don't think people had really thought about doing this before we did it. And the amount of energy we had to put in with these actuators at 5 kilohertz, it was actually a fair amount of that energy. Those things were pretty stout, I guess, for lack of a better word. So we were putting in a lot of energy at those smaller scales, and it was just able to suck that energy out.
John?
Yes.
Just as an observation, my whole career, basically laminar is good. So you want to have a controlled flow of anything so you can control it.
Yep.
And the disruption of it has never occurred to me that might have actual beneficial side effects like you were describing. It's really startling.
Yeah. I mean, it's very beneficial for mixing, certainly. The other thing that we thought that this experiment might have been useful for, although we never actually tested it, again, we're putting in some of the smaller scales, and by the time you get down to it, the larger scales have all been kind of dissipated, right? And so one thing we thought is, there are some aeroacoustic applications where you have large structures impinging on a surface and creating a hum or something like that, right? if you could dissipate those larger vortices with the smaller vortices, maybe this would have an acoustic application.
Well, not just acoustic, you might have a fatigue life issue too that you could reduce.
Yep, yep.
I mean, at that frequency, well, we know from our electronic boxes what can go wrong.
Oh yeah, that we do.
So John, I'm still looking for uses. I presume these same effects are going to occur in a liquid. So you could use it for homogenizing things like as simple as homogenizing milk or anything else.
Yep, you could.
So if you get to a much thicker, higher viscosity fluids, it'll still possibly work.
Possibly. The downside though is just higher viscosity means lower Reynolds number, which means it's a lot harder to get something to transition to turbulence, right? And so, you think of like stirring up paint, you really got to like, reef it around. Whereas like, you pour some milk in your coffee, you just go boop, boop, and you're done, right? So, yeah, I think it's kind of a question of the amount of energy you need to put in.
Well, like in heat transfer, you always want to get all that turbulent flow right at the IC or whatever it is you're trying to cool.
Yep.
And if you can increase that airspeed, and turbulence, you can get a lot of more convection. Sometimes that can make the difference between something that's going to work and something that's going to overheat.
Yep, and that was the whole concept of this guy.
Yeah. And we spent a lot of time looking at those kind of things over our careers. A lot of people do.
Mm-hmm.
I gather that's the big challenge with LEDs. I mean, they're remarkably efficient, but the energy, there's still some energy dissipated as heat, the IR range that you don't want.
Right.
And that's so highly concentrated if I try to get a lot of power.
Mm-hmm. Yeah, lasers as well. Laser diodes as well.
Yeah.
They dissipate a lot of energy into the substrate.
Very interesting.
Thank you.
There's so many things I can think, as I go through my career, my 46 years of engineering, I can think of several times when I've had to deal with fluid flow problems. And one of them was a submarine periscope.
Yeah.
One of my first jobs, it was my second job, it was at Cole Morgan. We made submarine periscopes, and we sold these things to the Dutch. And they had a submarine. They only had a couple of submarines, and they had put these periscopes on the submarines, and they shook sideways.
Yeah.
Like crazy. And it turns out that the vortex shedding frequency of the fluid, which is water, seawater, was exactly the same as the natural frequency of the periscopes.
Yep.
Yeah. So it cost millions of dollars to fix this.
Mm-hmm.
Then they couldn't really change the speeds of the periscopes and how far they came in and out of the sail. So they had to change the entire structure inside the sail to change the frequency of the natural frequencies of the periscopes.
Oh man.
Yeah.
So I have kind of an anecdote about that. If you look at an old car antenna from like the 60s or even the 70s, it's just like a cylinder of metal that kind of goes up, right?
Right.
If you look at one today, or most of them have it kind of built in now, but if you look at a more recent one, they have kind of like curlicues going up, spirals, right?
Yeah.
And it's exactly for that reason. Car antennas back in the day, it does the same thing. It sheds vortices and it gets a whistling noise. It's very annoying. And so you put these little curlicues on it, and it no longer does that. It breaks up the coherence of those wake vortices being shed. So you could have done something like that on your periscope. Probably would have fixed your problem, but I don't know how you'd retract it back into.
There probably might have been other solutions.
Yeah.
Yeah, you know, that is a solution. So in Germany, there is Thyssen, the company Thyssen has a experimental tower in the city of Rottweil, you know, where the Rottweiler dog comes from. And it's the largest tower in Germany, or the highest platform in the world, a visitor's platform. And they had a regular tower, but then they built a I don't know, it's like 5-6 feet extension to it and made it circular and put a kind of a mashed, I don't want to say fabric, I don't really know what exactly it is, but they put it in there in order to avoid the swaying of that large structure. So that's the same principle, isn't it?
Yep. Probably. Yeah.
And I gather that's the same thing on the Verrazzano Narrows Bridge between the two layers. The supports are very carefully designed to avoid Tacoma Narrows type failures.
Did you know the same thing happened to the Golden Gate Bridge? After the Tacoma Narrows, they had it almost came apart, and they had to change the they put up some aerodynamic changes into it that fixed it, but it was the whole thing could have fallen into the ocean. I just listened to a podcast about it the other day.
They retrofitted the Brooklyn Bridge too after that. So additional diagonal wires. That's the purpose.
Yeah.
The Tacoma Narrows Bridge that collapsed from airflow over it changed bridge designers' concept. And after that, they didn't use that design anymore, and it was because there was too much solid structure at the just below the road, the level of the road. And I forget where it was, but there was another bridge of the same design that was ready to open, and they didn't.
The Whitestone Bridge in New York was the same design, and they reinforced it so it would stay down instead of going up and down.
It was still fun to drive across on certain highly windy days because it would move a few feet. You could feel it. It wasn't going to fail, but you knew it was moving.
Yeah. Hey guys, I've got
in the river.
Hey guys, I need to drop off. But are there any more questions? I got time for about one more.
Yeah. Okay. Do you think your son's going to win his baseball game?
Well, it's just a practice. So yeah. Who has the idea of having 10-year-olds practice baseball from 8 to 9:30 on a school night? I don't know.
Well, thank you, John. That was awesome.
All right, thanks. I enjoyed it.
John.
Really nice. Really nice.
Thank you.
All right.
I want you get your screen back to us.
Okay. Share. Hold on.
I can probably do it. Let me see.
Yeah.
Options view. Stop participants sharing. There you go.
Yeah.
All right.
Cool.
Well, thanks.
All right. Thanks, guys.
So we're yeah. If anybody would like to do a talk, we have Ed's going to do one. We're scheduled all the way through the 12th, and Ed's going to do one on one of those. We have 2 dates that are open, and we could do a three-man another one of these 3 presenters things. Dan Rosignol said he would do one, and if we got 2 others, Howard, you must have something you could do about computers for 10 minutes. The latest and greatest.
I could figure something out, or if you want to talk about cars and motorcycles.
Sure.
Yeah, that's great.
Yeah.
That would work.
I've been trying to get somebody to do one on horseshoeing, actually.
If anybody has any good questions, burning questions about any of that, let me know and I'll see if I can be prepared with some kind of organization for it.
How about electric motorcycles? Are they going to happen?
They already are. I was at the motorcycle store today where I hang out, one of my customers, yesterday, actually. And there was a Harley parked outside that was an electric Harley. It was very, very unusual looking.
I just think the history of motorcycles would be interesting. No,
That's
Yeah,
good.
if you do motorcycles, remember Glenn Curtis in 1907, 137 miles an hour. 1907 on a motorcycle he built himself.
yeah. And Scott Diamond could do one on the history of bicycles.
Yeah, it'd take a lot of work.
Would take a lot of work. But if it's only 10 minutes, you could do it like a speed.
If I could think of something, if I think of something cute, I'll let you know. But
All right.
it's got to
Anyway,
involve robots.
Yeah, we're in pretty good shape for talks right out through May 12th. So I think that I don't know if we've ever had this many talks, but it's
Oh, that's good.
Yep.
Doesn't seem to be dying, right? How long's this been going on for?
It's been going on since last April.
Yeah. Well, so we're getting close to a year now, right? Yeah.
Okay, which date is the first anniversary?
Exactly, but it's actually we should have a celebration.
Yeah, it's pretty astounding, right? I mean, not quite every week, but almost, right?
Yeah. I'll figure it out. I'll figure out what it is, and when we're famous, we can go back to the this is the date. Maybe make it a national holiday. All right, everybody. Enough of that. So enjoy the spring. We had beautiful weather here today, and hopefully the rest of you will too. So
bye.
Thank you.
See you next week.
Thanks.
Thank you.